Welcome everyone to our webinar, End of Life Textiles, Understanding the Role for Biotechnology in Developing a Circular Textiles Industry. My name is Dana. I'm the Knowledge Transfer Manager for Synthetic Biology at Innovate UK Business Connect. So we recently changed our name from KTN to Innovate UK Business Connect. And this event today is in collaboration with the Bioeconomy Cluster Builder. So I'm joined by Kim Cameron from IBIC. And the webinar is delivered under Innovate UK's Sustainable Bio-Based Material and Manufacturing Program, short SUSBIO-MM. Quick reminder of the housekeeping rules. You are muted throughout the webinar. And if you have any technical issues, please use the chat box and we will try sorting them out in the background. And also use the chat box to say hello and introduce yourself. It's always great to know who's in the room and who's joining us today. If you have any questions for our speakers later, please use the Q&A box and we will ask them during the panel discussion. And as a reminder, the webinar is being recorded and you will be receiving the link to the recording together with the copy of the presentation in a couple of days. Okay, we have a really great agenda lined up for you. So in a moment, I'm going briefly to introduce the Sustainable Bio-Based Materials and Manufacturing Program, and then handing over to Kim to introduce and give a brief introduction to the Bioeconomy Cluster Builder. And then we are really going to dive into today's webinar and why we are here. Personally, I find those statistics from textile waste really mind-blowing. We produce about 93 million tons of textile waste every year, and more than 80% is going to landfill and being incinerated. So we are only using about 20%, and we really must do better. And we must fill this loop and ensure we are not losing those 80%. And to create a really circular textile industry, we must reconsider how we're making our textiles, but also we must reconsider the whole supply chain and taking end of life into account. And in today's webinar, we have some really great speakers addressing this and how to close the circular loop. So we are going to hear about groundbreaking technologies alongside biotechnology. And our speakers are going to explore those technologies. And we are going to hear about smart innovation in textile sorting. We are going to hear about textile waste biorefinery and how we can use those lost resources and making sure they are not being lost instead, and they're being used for new products and in new processes. So we are having 4 presentations lined up for you, and then we have a panel discussion at the end, which is chaired by Lynn Wilson, and then we are hoping to wrap up around 12 o'clock, and there will be some further information around funding opportunities. Brief introduction to us. As I said, I'm working for Innovate UK Business Connect. We recently changed our name from Innovate UK to Innovate UK Business Connect. We are part of the Innovate UK family. So our role is really to connect innovators from across all sectors to new partners and new opportunities. So helping them to accelerate and bring their project and products and processes to market. I'm part of the chemistry and industrial biotechnology team, and we are currently leading on a project around sustainable bio-based materials and manufacturing. Materials and manufacturing are really important for the UK economy. And you're all aware we have a growing world population. That means there's a growing demand for materials. And to align with our ambition for net zero, reducing the impact on climate, we need to reimagine how we make our materials and how we manufacturing those. And bio-based materials and biomanufacturing provide a really great opportunity for this. So within this program, we are looking at bio-based feedstocks, sustainable biotechnology, innovative bio-based products, feedstock recycling, and biomanufacturing. And today's event really fits into this, especially around the feedstock recycling. As I said at the beginning, we are currently producing 93 million tons of textiles waste every year, and 80% are going to landfill, being incinerated. And we need to stop looking at those as waste, instead considering it as a feedstock and taking up the opportunity to recycle them, reuse them, and making new products out of them. So personally, I'm really looking forward to today's event and hear what our speakers have to offer and the solutions they are providing in this area. But before I'm going to introduce our speakers, I'm going briefly to hand over to Kim to introduce the Bioeconomy Cluster Builder.
Thanks, Dana. Morning, everyone. As Dana mentioned, I'm Kim Cameron. I'm one of the business engagement managers at the Industrial Biotechnology Innovation Centre, or iBioIC. And for the last 4 years, we've had the pleasure of collaborating with Innovate UK Business Connect on the Bioeconomy Cluster Builder. So the initiative has 3 main aims. The first being to raise awareness of the different applications of biotechnology, so all the great things that you can use industrial biotechnology for, and also to bring people and resources together to support new ideas and develop new value chains. And so that aligns with what we're here to do this morning, to raise awareness of what you can do with IB and to connect people and resources. And lastly, we encourage the utilisation of Scotland's bioresources. So these are essentially the raw materials that you can use as feedstocks for biotech processes. And at iBioIC, we host the bioresource mapping tool, which has data about the locations and quantities of various feedstocks around Scotland. Next slide, please, Dana. So in addition to events, the BCB offers a range of support. We leverage the networks of the partner organisations to provide technical and commercial support. And similarly, we convene challenge-based roundtables and focus groups, bringing together stakeholders that can help companies move forward with challenges that they have. And we offer signposting to different sources of funding, both grant funding and a network of investors. And lastly, as I already mentioned, we provide information on feedstock supplies. Next slide, please, Dana. Oh, sorry, if you go back one, sorry. So my contact details are at the bottom there, and also the web address for the cluster builder. Thanks. And so just signposting to our next event, which is very much complementary to today's session. On the 13th of March, we're hosting a networking event for stakeholders in the textile and biotechnology communities. And this is part of Bioeconomy Week Scotland. And they're taking place in the Student Union at just go back. Thanks, Anna. Student Union at Strathclyde University. And the QR code in the bottom right-hand corner, you can find more information about that event and also details of how to register. So please do come along if you're free. We're running this in collaboration with the Glasgow School of Art, School of Innovation and Technology. Thanks, Dana. And that moves us seamlessly now on to a plug for iBioIC's conference. So the event that I just mentioned is running the morning prior to our conference, which starts the afternoon of the 13th of March at the Technology and Innovation Centre in Glasgow. It's our 10th year anniversary, so we'll be looking back at all the great things that iBioIC and our stakeholders have achieved in biotechnology over the last 10 years, and then looking ahead to future developments. Registration is open now. There's a QR code on screen if you want to use that to find out more. And then the web address, dedicated web address for the conference is in the bottom left-hand corner there. So it'd be great to see you. And that's me, Dana, I think.
Thank you, Kim. And I'm delighted to introduce our first speaker, Len Wilson from Circular DS. Lynn, if you would like to share your presentation.
Can you hear me okay?
Yes, perfect.
Thank you. So thank you so much for this opportunity. So I'm Dr. Lynn Wilson. I'm a consultant, the founder of Circular Design Synergy, and I'm also an academic researcher in the Adam Smith Business School at the University of Glasgow, where our key focus is consumer behaviour and textile circularity. And I thought today what I could bring to this session was just to centre textile in its relational and systemic approach in society. So just thinking about, we are in the age of the Anthropocene, where textile in all its wonderful form is a celebration of our personalities and our cultures, and operationally it supports us to do so many things, and it touches every area of our life. So textile is essential to our lives, and in that respect, why I wanted to start with this was to think about all of the different solutions for all of the different challenges and applications we have for textiles in our life systems. At Circular Design Synergy, our belief is that there's no such thing as a sustainable material. There is only a material in a circular system. And without that, without a system in place, there is only the element of waste. And we have no idea where things are actually going. So I recently, a couple of years ago, completed my PhD research, which was based in Scotland, where Zero Waste Scotland produced a report saying that 32% of carbon emissions in households was from bin textiles. This number is a bit controversial, and there is a different number which says it's around 17%. But whilst we can argue about percentages, there is no doubt that the current circular systems are not working, and not working for consumers at a stage where we need to reduce textile clothing consumption and improve clothing reuse and the reuse of textile already in use. So as I said, I started by talking about we're in the age of the Anthropocene, means that 8 to 10% of carbon emissions are caused by textile production. 20% of global waste is caused by textile production. 92% of India's water supply is polluted by the production of textiles. And up to 25% of production in a product such as garments is wasted in the design at the design stage. And of course, we know that particularly in apparel, that market is 65% dominated by crude oil-based fibres. And the majority of this production is in the global south, whereas we know that in terms of consumption, the 800 billion garments, for example, that are circulating are in the main in the global north, where at least, say in clothing, 40% of the average wardrobe is never worn. And 92 million tonnes of textile are landfilled globally every year. So this transition to a circular system and a circular material chain, for me, as a consumer behaviour specialist, what I'm really interested in is recentering consumer as the ignored key stakeholder in the textile value chain, because without understanding where a textile ends up, and so in the consumer use cycle of maintain, store, use until end of life, we really need to understand what consumers are doing with textile, that leads it to end of life and the state that that textile is in order for it to be part of a reuse or a processing system. In terms of relationships and systems design, we look at it from 3 different pillars, from holistic relationships, which is really about keeping textile in use for as long as possible from the micro to macro level, and that requires biotechnology in terms of new chemical-free or less chemicals to enable the maintenance and storage of clothing or textile. In regenerative systems, whilst it's about organic matter and end-of-life composting, this is really only sustainable by growing new crops and farming. It's only sustainable with reduced consumption. And then, I don't want to dwell too much on the technical, because I know that we're going to hear a lot about that today in these presentations, but I really want to emphasize the holistic side and to move on to talk about examples of holistic practice that we're possibly all involved in and we take for granted. And in terms of a bioeconomy, it's about how that bioeconomy can support the longevity of garments and textile so that we can have these systems of keeping products in use for as long as possible. Just looking at the bottom left-hand corner in the research I did, which was qualitative, going into people's homes, into their wardrobes, their drawers, into the laundry baskets, asking them really personal questions about what was going on with the textile and clothing in their households. And for example, here, socks, an eternal issue with things wearing out, small garments wearing out, or holes in garments, or garments not fitting. And so it's thinking about how do we design new materials, how do we design materials that are part of a circular system, a regenerative system that works with consumer product. And then we talk a lot about scale and the scaling up of technologies, but I again want to appeal to the community element and to really ask about scale and to say we have a critical mass of communities who are really trying to address through their own models of reuse and repair training in communities. And so how are we working with at that micro meso level to solve this textile crisis through looking at different communities and not entirely obsessed with scale and scaling up technologies. And then ACS Clothing, probably well known to most of us, but they have this fantastic ozone chamber, which means that they're a chemical-free cleaning rental service provider for a broad range of companies. And again, another brilliant example of how biotechnology can really address the keeping in use, the circulation of textile, rather than straight to end-of-life processing. So for me, it's about how we keep that stock in use for as long as possible. And in the research, in terms of findings about what consumers are experiencing, pathogens, pathogenic staining, engaging with bacteria and chemicals in clothing, chemicals in products, skin products, creates staining in clothing that can happen very quickly. And again, then consumers are challenged by how to get rid of those stains, how to work with those stains to keep clothing and textile in use for as long as possible. Moth infestations, we spend 90% of our time indoors now during the pandemic, up to 100%, but our cleaning regimes, our systems of cleaning are very different from what they used to be. So we have a lot more bacteria attractive to insects increasing in our homes. And in order to retain a holistic biosystem that's working in harmony with insects, rather than trying to eradicate them, it's how do we support consumers to manage cleaning systems, antibacterial systems? Because what we do find is that consumers want to keep products in use. They are what we say is prosuming. They're reusing, they're repurposing the textile that they already have. So what solutions can the biotechnology industry come up with to really support consumers keep what they have in use for as long as possible? We're living in an age of what I have termed anti-fibre poverty, where 65% of what we use is polymer-based. This is not always healthy for our skin and our well-being in terms of thinking about designing systems of textile use. Of course, we always want a natural fibre next to the skin, but most of us will be UK-based, and so we want a really great, probably polymer-based, waterproof to keep us dry. But what's the future? What are we transitioning to in terms of these biotech fibres? But how are we thinking about end of life at the design stage of these new fibres, and where are we implementing them? I see a lot of new biotechnology materials that are immediately showcased in luxury fashion. And I think to myself, is that really the best use of new materials that are replacing polymer? This is just an example of when we were doing our research, that we were looking for the disconnect and the misalignment between what consumers are doing and what the industry is doing to see why so much clothing and textile end up in landfill. And we could see that consumers go through a similar micro-segregation process to the macro-textile sector. But as individuals, we all have different ideas of what is clean, what is dirty, what is reusable, what is usable. And I've just put out this little provocation here from a participant's jeans. And yesterday I asked a whole room of 60 MSc students what they would do with these jeans. And again, it was a very mixed bag. Everything from saying, well, actually, these jeans are the height of fashion, and we could actually wear them or resell them, to no, it's definitely time to get rid of them. So in summary, what we find with consumers, they're still putting a lot of textile in the household bin, particularly small cotton items like undergarments, because they believe that that's the only place for them to go. They're completely confused about what needs to be put in the clothing banks or in areas where textile can be recycled. There's a lot of education needed there. Donating to charity is the preferred option, but it means only in a local area, 50% of what's donated to charity will be resold, and the rest, again, is going to either overseas markets or unknown areas. Resale platforms are increasing, and interest in resale is really increasing. And so that idea of keeping textile clothing in circularity needs those biosolutions to ensure that products can be kept in use for as long as possible. I think that's sort of more recommendations. Yeah, as I said, practical use for clothing banks. And again, looking at that community-led clothing circularity initiatives, how can the bioeconomy help at that local level? And how can we readdress the challenges related to scale, scalability? We do need scale and scalability, but we also need a broad range of solutions to engage everyone in this challenge. And finally, I just wanted to say that there is more information in our white paper that we presented to Scottish Parliament last year, which outlines our research and evidences some of the recommendations I've given here. And this report is finally part of a subgroup at the Scottish Parliament, and please get in touch if you would like to know more about the workshops that we'll be holding as part of the Scottish Parliament Circular Economy cross-party group on textile circularity. So thank you very much. We'd love to work with you. We'd love to know what you do, and we'd really love to get involved. And thank you very much for listening, and I look forward to hearing speakers and questions later. Thank you.
Thank you, Lynn. A really great kickoff to the webinar. Really interesting angle. I'm now handing over to our next two speakers. So it's Flor, a senior program manager at UKFT, and Cindy, founder of One Again. Flor, if you would like to share your presentation, please.
Yeah.
And if you have any questions for our speakers, please use the Q&A box and keep them coming.
Thank you, Dana. Can you see my screen?
Yeah, all good.
Okay. Thank you. Yeah, so today we are here to present you an introduction of the automated circularity in textiles, the ACT project. And Cindy and I, we are today representing the consortium for the project. And I'll start with the So today we are going to talk about the ACT project, which is a 2-year project that is funded by Innovate UK and is led by the UK Fashion and Textile Association, UKFT. We will go through a bit of background on why ACT project was created, the ACT project consortium, what we are working on in this project, and also some collaboration opportunities that everyone can engage with. And then we will move towards what is going to happen in the vision for the project beyond these 2 years. So everyone is aware that the volumes of end-of-use textiles are increasing year on year, not just in the UK but globally. But in particular for the UK, we have recent numbers of 1.3 million of tons of end-of-use textiles generated every year. And the reality is that the majority of those textiles end up in landfill and incineration, and a small proportion is diverted to as wearable textiles, which means that they can reworn or be resold. But we estimate that a big proportion of that could be utilized for recycling into textile-to-textile process. So in this diagram, we can see the part that is highlighted as blue and green. That will be approximately 75% of those end-of-use textiles that could be either reworn, resold, or, as I was saying, suitable for recycling. But then that is not happening today. And the reason why is not one of the reasons why it is not happening today, it is because the textile ecosystem, it is based on a linear model, and part of the bringing those textiles back in the loop for reuse, it is based on manual sorting and pre-processing, which is really costly, and it doesn't happen at the speed that is required to supply to textile recycling process that are either currently development because of this reason, or that they cannot develop because of that lack of consistency of the feedstock that we can provide to them. So this is the reason of being for the automated sorting for circularity in textiles, the ACT project. The main purpose of the project is to provide a solution for implementing the sorting and pre-processing of end-of-use textiles into textile-to-textile recycling process. So in the ACT UK project, we are looking to build the blueprint of an ATSP. So the ATSP is what we call the Automated Textile Sorting and Pre-Processing Facility that could have under one roof all the technology that will be required to sort textiles by color, fiber, quality, composition, eliminate the disruptors from those textiles, and pre-process them in a way that they can be suitable for the different textile-to-textile recycling technologies. Because each of them, this is an added challenge into this, each of the textile-to-textile recycling process have their own feedstock specifications. So this is the purpose of the project. And in the project consortium, we count with stakeholders from all the different areas involved in this particular topic. We count with industry associations like UKFT, CRAB, Textile Recycling Association, technologies like Circle A, Born Again, IBM, and manufacturers, collectors, sorters, research and academia, and retailers and brands, to make sure that everyone is bringing their knowledge and their expertise to find a solution that can work. Right. So in terms of the approach of the project, I wanted to introduce what are the key topics that the project is working on. And as we have seen in the previous slides, there are different areas in that textile ecosystem that need to be engaged for the automated sorting facility to be deployed successfully. One of them is the consumer side. So in app, we are working to optimize the ways that we collect garments from consumer, understanding as consumer the citizen itself, or also retailers, brands, other or city councils and other organizations that could collect these data as well, and how we can optimize the logistics to provide those data to the future ATSP. So at the moment we are running trials with some of the retailers in the consortium. We are also looking to develop a database of global innovations and case studies around collection of post-consumer textiles. And we are also going to do industry roundtables where we will connect with not only the people that we have in the consortium, but also external organizations here in the UK and in other parts of the world to bring the knowledge around this topic. And then we're also looking into the technology development that is required to create this blueprint for the ATSP. So we are looking at the state of the art, what is currently out there in terms of equipment for textile identification, conveyance, disruptor removal, and size reduction, because this equipment will inform the selection of the equipment for the first ATSP in the UK. And as part of that, we are also looking at emerging technology. So technology that it is currently under development, but that we could find ways to further develop it so that in the future we can improve the equipment that will be part of the ATSP. And of course, as I was saying, the blueprint, which is at the heart of the project, the creation of the group ATSP, and as part of that, we have already started looking for the first for the site that could host the first ATSP in the UK, and Cindy would talk in a bit about that in detail. And then we are also looking at the infrastructure. So how the textile industry infrastructure needs to evolve in the UK to provide a successful transition from manual sorting to automated sorting. So here we are looking at the market review for the non-rewearable textile flows in the UK. We are engaging with textile manufacturers as well. We're doing trials with recycling post-consumer textiles to different methods, mechanical recycling, chemical recycling as well. And we are looking into skills training required to support that transition from automated from manual to automated sorting, as well as manufacturing capacity in the UK. I would like to share with you some collaboration opportunities that we have as part of the project. So we have recently launched the ACT newsletter and the ACT website. You have the QR code on the screen, and through those two channels, we will be able to communicate progress on the project as well as further opportunities for collaboration. At the moment, the ones that we have open are the knowledge database. So we have the innovative textile collection and logistics database. RAP is currently working on that one. So I will encourage everyone that if is actively working on this topic or that has information around this to contact RAP. We have the email in the screen. And we also have two upcoming opportunities to engage with the project. One is a workshop that we will be doing this spring that will be looking into the non-rewearable textiles in the UK. What are those current and how we would like them to look like in the future. And then June this year, we are looking to host an industry roundtable as well. In this case, these two opportunities, both the workshop and the industry roundtable, are focused on post-consumer textiles and collections and logistics. But as I was saying, during the project, we will have other opportunities for engagement as well. So I'll suggest that everyone stays in the loop and join that newsletter. And of course, if there's any question or you would like to get in touch, we have the sustainability email address from UKFD, which is the lead organization, and you can contact to us through there. And now I'm going to hand over to my colleague, Cindy, that will talk to you about the long-term vision for the automated sorting in the UK.
Thanks, Flor, and thanks to everyone for joining today. Yes, this is about the long-term vision, but I think I'll start by taking a step back and why we believe ATSPs are needed in the UK and actually everywhere. And with the company I founded, Warren Again, about, well, back in 2005, but in 2012, we started the development of a polymer recycling technology for non-rewearable textiles for polyester and cotton. And the process itself is able to separate, decontaminate, and extract the polyester and the cellulose from cotton. And it's been a long road of development, but we're getting closer to industrialization. And specifically in the UK, Circulate, a new company that was formed 2 years ago, is the official partner to license that technology here in the UK. And we will be building a first 50,000 ton per year plant in the next few years. Now, the most important thing when you're working in chemical or mechanical recycling is, where are we going to get the feedstock from? And that indeed is where the idea for Circulate and why it came into existence. Really looking at all of the non-rewearable textiles today that are generated in the UK and where they're going. Most of them are being exported. A lot of them are still going to landfill, and really it's the economics that's driving this. So in order to get these textiles into fiber-to-fiber recycling, we recognize the need for transitioning from manual to automated sorting. And that's where the idea for the ATSP came from. And Circulate is a partner in this ACT project. And we're very much focused on moving the UK from where we're at, quite a lot of waste, to fiber recycling, with the ATSPs being the first step in this. And we're also really pleased that with this government grant, it's really been instrumental in bringing stakeholders together to actively shape this pathway and actually look at the commercial steps to getting us there. So where we're at today, we are right in the middle of the project. It is finished in March of 2025. This phase that we're in now is all about the development of the first industrial scale ATSP, where non-rewearable textiles come into the facility. They're separated by fiber, composition, broken down, buttons, zips, other disruptors are removed, and then they leave the facility as feedstock for the range of recyclers. And that can be worn again's process, chemical recycling. It's also for all the other recyclers that are focusing on fiber to fiber, whether it's mechanical, chemical, or other processes that are in development, either existing or emerging. So moving forward, though, we know that with these high volumes of NRT, non-rewearable textiles in the UK, we have huge volumes that could be transformed into feedstock for recycling, and we need these ATSPs to do that. And working on the numbers that Flora introduced at the intro, with 620,000 tons of non-rewearable textiles, breaking that down into numbers of automated sorting facilities, we have somewhere in the region, well, enough textiles to go into at least 12 automated textile and sorting pre-processing facilities. So it's you know, the feedstock is out there. The industry is waiting for it, but there's a lot of work to do in terms of restructuring the infrastructure, rechanneling the flows of materials, and making sure that the economics work at each step of the process. So if we go to the next slide here, Flora, thanks very much. So the long-term vision, but we're working on it today, has multifaceted benefits. And it's really worth highlighting here that this isn't just about finding solutions for textile waste, you know, and just doing the right thing. It's actually about realizing that these materials can unlock a whole new industry of raw material production right here in the UK, you know, turning what is currently considered waste into a resource that can be integrated back into supply chains around the world. And it really is multifaceted, from the social perspective, environmental, jobs, the economics. Literally, we would be going from virtually no raw material production in the UK today to turning hundreds of thousands of tons back into raw materials, replacing the use of virgin resources. And all in all, we see ATSPs really as a crucial stepping stone to enabling this industrial revolution in hopefully the not too distant future. Also important around this loop here of benefits is that this system is driven by incentives that drive the behavior change, not just to consumers, citizens, but also to all the businesses involved in making this happen. There has to be a real economic driver for it. And underpinning all of this absolutely is legislation, and making sure that government is involved in the stepping stones, in supporting through legislation how we get to a fiber to fiber role. And on that, I will close and say thank you very much.
Thank you, Cindy and Flora. Really great presentation. And maybe in our panel discussion later, we can pick up some of the points you made, you know, especially around, you know, building the infrastructure, scaling up. And I'm hoping there are some policymakers in the audience and listening and, you know, putting the incentives in place. And yeah, let's pick that up during the panel discussion. We are now moving a bit more into the biotechnology part of solutions and innovations. And I'm delighted to have Professor Chen Yidu from the Department of Physical and Life Science, University of Huddersfield, joining us and talking about the textile waste biorefinery. Chen, over to you.
Okay, good morning, everyone. So my name is Chen Yudu. I'm a professor in biochemical engineering in the University of Huddersfield. And thank you for the invitation to talk in this webinar. Here, I would like to introduce some of our research work, and we want to develop a biorefining strategy. We hope this one could help to tackle the textile waste problem. I think several of our previous speakers already mentioned about the textile waste issues. Quickly, I just go through some of the facts. So we have quite a lot of amount of textile waste, which equivalent to about one truck load every seconds go to the landfills or incinerations. And then half of them are plastic, and half of them are the natural fibers like cottons, wools, and other things. So the textile waste in the textile production is not only generate weight, but in the production process also contribute greatly on the greenhouse gas emission and also usage of the water resource. So they use quite a higher amount of the fresh water. So fresh water also a valuable resource that normally are ignored, especially in the UK. We have lots of rainfalls recently. So the we spend a lot of energies and then spend a lot of resource to make textile. But when we finish the textiles, and then lots of them have been going into the landfills or incineration. So this based on a recent statistic, it's only 21% has been recycled and reused. And in the UK and in the US, it's slightly less than that. So I have to highlight, so this 21% or 15% are mainly working on the, let's say, recycle, let's say, after the textile usage is donated to charities and then reuse, resell for the charities. And some of them, the textile has been downgraded to use like stuffings for some other applications. There are only about 1% of textile actually recycled to make a new clothes. So the textile have been recycled to using new clothes. It's less than 1%. It's a really, really small amount. To recycle textiles, there are quite a lot of technologies. It's already developed or on the stage of development. So it's a quite a complex and then difficult process. It's mainly because of textiles are so diverse. We use different materials, we use different associates, and then have different colors. So most process need sorting, and then after that, some of them can be reused, that will be good. But some of them cannot be reused. They have to go through different cycle, like mechanical recycle. But mechanical recycle, they are mainly suitable for a pure, let's say, material made to the textile, let's say pure PET. It will be relatively easy to recycle it. If it's a pure cotton-based material, it can be shredded and then make into the fiber. But lots of clothes is not a pure products. It contains both the man-made fibers and as well as the natural fibers, cottons. They blend them together. It's going to be difficult to go through the mechanical recycling. For the chemical recycling process, they break them down into small molecules. So, and then from the small molecules, they use for different applications. Some of them can be reused to make long-chain polymers and then used for textile application again. But this spend a lot of energy need to do that. So among all of them, they will be some other issue like the dye. So the dye we use to make the textile attractive, but when we recycle the textile material, the dye starts create some problem. So based on that, we want to develop a biorefining process like biorecycling technologies. We aim to recycle both the PET fibers and also the bio-based fibers. Basically, the technologies is based on, let's say, when we got the tactile waste, and then we mainly want to using an enzyme called cellulase to break them down the cotton part. So the cellulose into some sugars, and then from the sugars, we ferment them into platform chemicals, and then using the chemicals to make something useful, as well as to making new fiber. And then the enzymatic hydrolysis conditions is mild, and then the PETs are not damaged, and then they can directly recycled and then reused to make PET fiber. So the cellulase itself is quite expensive, and then we consider whether we could using a tactile waste to produce our own cellulase. So the ideas is mainly derived from my previous research. So in my previous research, we're using cellulose to degrade the biomass to produce biofuels. So because we consider the cotton fibers is another type of cellulose, and then it's probably, yeah, we can try such process, and therefore we developed, we call it the first generation for biorefining process. So we tried different fungal strains, and then to see whether we can produce cellulase using the tactile waste material. And then we can see after a few days of cultivation, we can visually see some fungal growth on the textile. And then if we see more closely using the electro scanning microscope, we can see on the left-hand side, this before the fungal fermentation, and after a few days, some fungal colonize on the surface of the fibers. They grow happily on the top of the tactile waste. And then we tried the different tactile waste, let's say 100% cotton, and then mixture of cotton, and then plastics, and then some cottons has been, some tactile waste has been manufactured differently. So we can see most of them, they produce a reasonable amount of cellulase. So even to our surprise that only the man-made fabric, the PETs, they can still support some of the fungal growth and then produce some cellulase. And we selected the best one to go ahead to see we can produce cellulase, and then use the cellulase to like enzyme to hydrolyze the cotton part of the material. So this one shows about the fungal growth in the specific tactile waste, and then we can see before inoculation fungal growth. So the fiber is quite clean, and then we can visually see some fungals colonize in the fibers. So along with the fungal growth, they produce some enzyme. So as well, so as the enzyme production, so the enzyme already start to break down the cellulase, and then make the fiber a little bit weak, and then this help for the next stage hydrolysis. Once we got the enzyme, we analyze the enzyme composition. So from the composition analysis, is the enzyme solution we get contains all the essential subunit for the cellulase degradation. And then we compare our own enzyme. So on the right-hand side, top diagram, so the fungal enzyme is our own produced, and then we compared with a commercial enzyme. So definitely commercial enzyme behave better, but our enzyme after a certain time, it's catch up. So similar levels or slightly less than the commercial enzyme, but our own enzyme produced in-house, it have a kind of a low cost, it's relatively cheap. So here shows about the hydrolysis results. We're using a mixture tactile waste that contains 60% of the PET and then 40% of the cotton. So after hydrolysis, we can see in the microscope, some cotton fibers has been degraded, and then left over only the the PET fibers. So this is a plastic fiber. And then here is another diagram using the electronic scanning microscope. And then on the left-hand side, we can see it's a mixture of fibers, contains cotton fiber and then PET fiber. After that, it's quite pure. It's mainly the PET fiber. And then we, on the first generation of this biorefining process, we aim to produce glucose. And then we can see after process optimization, we can reach nearly 100% glucose recovery. So that means all the cotton fibers and has been converted into glucose. And then in the next step, our collaborator, Professor Caroline in Hong Kong City Universities. So in her group, she converted the glucose that produced into some other chemicals like lactic acid. And then from the lactic acid, we make a polylactic acid. Polylactic acid is a kind of fiber can be used to make clothes. We also have a collaborator, Professor Xiaoyuan Liu from Hong Kong Poly Universities. So he collected the leftover PET fibers and then to make the pellet, and then from the pellet to respin into the PET fiber and then dye them again to make a new textile products. So we put this idea into the 46 international exhibitions of invention at Geneva. And then we were quite happy to receive a reward about the gold medals. And then they just it's very encouraging to develop this biorefining process for the textile waste recycle. So based on that, we consider about the enzymatic hydrolysis completely break down the cotton fiber into sugars. The sugars is still a small molecules and then go through fermentations. It's a long process. So we consider whether we could bypass that. So instead of completely degrade the cotton fiber, so we want to, let's say, just degrade them slightly into a short chain cellulose. And then from the short chain cellulose, we directly make into the cellulosic fibers and then can be used for a textile application. So we call this one is the second generation of a biorefining strategy. So we put these strategies. We are quite happy to receive some award from the BBSRC and the EPSRC. So we recently won a reward on the scheme about the plastic recycle research fund. And then we got about 1.8 million support us to further develop the idea. Basically, we want to develop an integrated waste refinery idea. So from textile waste, we want to recycle these plastic fibers and then these cellulose fibers and then recycle dyes. And then the thing that we cannot recycle, we want to convert it into heat and power. And then we want to use that to make a new textile product. And then the ideas is that we firstly start from AI assistant with a sorting process. We have colleagues from the computer science to working on the AI assistant with sorting. And then me and my colleagues, Professor Jason Hallett from Imperial College London, we are working on the separation of the cottons and then the plastics. So we're using both ionic liquid extraction method as well as the enzymatic hydrolysis method, basically to separate the cotton fibers from the plastic fiber. And then we have colleagues working on the fiber formation and another colleagues working on the energy recovery. We also have colleagues working on the life cycle assessment to see which steps could be further improved and which steps is more environmental friendly. And then we have some industry support from trade is a charity the textile recycle charities, and then we have companies, research and development company called the Dye Recycle. And then these companies will support us on whether we can recycle the dye through the ionic liquid process. We have UKFT support. It's a platform will be able us to talk with the industry in the fashion and then textile industry. And then we have manufacturing companies. So these companies will support us on a pilot plant trial at the later stage of our development. We also have 3 industry and academic external advisor, so they will help us to shape our research and then in the next 3 years. So this project we just started in November last year, so it's just started recently. Hopefully in the next few years we will report more exciting research outcome. So by the end, I would like to thank my sponsors, mainly EPSRCs and then BBSRC, to support this type of research. And then thank you very much for listening.
Thank you, Chen. You really great presentation, and I love that you are basically closing the loop on, you know, applying different technologies coming together and addressing all the waste materials in the textiles. Really great. Okay, last but not least, we have our next presentation, and we often, when we talk about textile, we often think about clothing, but textiles are in other products like sailings. I'm really looking forward to the next presentation by Dr. Joe Penhall-Smith. He's the CEO of Sustainable Sailing, and I hope Joanna is on the call. Yes, hi, Joanna. BBSRC Discovery Fellow in Biotechnology, University of Edinburgh. Over to you, Joe and Joanna.
Okay, hopefully that should all be nice and visible.
Yeah, if you can just put it in full mode.
Lovely.
Yeah. You need to switch around at the moment we can see the preview.
One second, I will just share the correct screen. There we go. That should be right.
Yeah, we just go into presentation mode.
So sorry, I just got stuck. There we go. Yeah.
We can still see your presentation mode, but it's fine. You want to go ahead?
That is quite annoying. Oh well. Hey. So sorry about that. So my name is Joe Penhall-Smith. As I've just been introduced, I'm one of the founding directors of Sustainable Sailing and the current driving force behind the R&D department. And so what we're going to talk about a little bit is some of the work we did last year with Dr. Joanna Sadler to combine an existing recycling system, our cell recycling system, with some novel biotechnology. So very briefly, we'll have a quick chat about who Sustainable Sailing are, who Joe's lab is, and the kind of scale of the challenge, and our existing technologies, and then talk a little bit more in a little bit more detail about the integration of these recycling technologies with, a potential metabolic upcycling and engineering biology approach, and from there, where we're going with that afterwards. So, sustainable sailing. We are the world's leading sail recycling company, and our recycling technology we've demonstrated is capable of recycling 99% of all sailcloths on the market. The only thing we can't currently recycle is cotton-based sails, and these are a very small proportion of sails ever being sold anymore. And on the back of that, we were the Institute of Engineering and Technology started the year last year.
Sorry, Joe, there just came a suggestion from the audience. If you go on display settings and pick swap display, that should improve your. Sorry about this one. Give us a second to sort it out.
So I think on the screen we were just on, Joe, there was a little display settings option.
Is that better?
Yes, that's great.
Yeah. Thank you.
Really easy solution. Sorry about that. Sorry, Joe, if you would like to introduce yourself.
Yeah.
That's fine, Joe, go ahead. I'll introduce myself a bit later when I come on.
Cool. And so Joe's lab is particularly kind of focused on this multidisciplinary approach to chemical recycling, and particularly the upcycling of different polymers was one of our areas of real interest. So the challenge in terms of the marine industry, there are quite a lot of sails. So there is a deceptive amount of sails being built every year, about 13 million square meters, according to the work by Resale a couple of years ago now, which is fairly approximately the same square area as London, they attribute. And this is a kind of growing problem, somewhere between 2 and 3% growth in terms of sale of sails in the leisure marine sector. And sails are becoming rapidly more popular as a decarbonisation method for particularly large-scale shipping. If you put sails on your container ship, you need to spend less money on fuel, and this is quite often in this kind of industry the difference between a profitable journey and not. So, in addition to this, in effect to add insult to injury to quite a large problem in terms of volume and area, the complexity of sails doesn't really help anything. So we get everything from your traditional woven polyesters and nylons, often with additional UV coatings and stretch minimization coatings, all the way through to high technology composite sails, carbon fibres, dynemas. However, the vast majority of them use polyethylene terephthalate as either binding resin or as the woven fibre. So, as I've mentioned, quite complex in terms of what we're actually making a sail out of. And in addition to that, there's a lot of UV resistant and additional coatings and dyes on a lot of these sails to allow them to survive extended exposure to the marine industry. Which does mean that current chemical recycling technologies particularly are less appropriate or get chemically poisoned by these additional coatings and this additional blended polymer complexity. So it does mean that while there are recutting and repurposing organisations out there who can take your sail at end of life and turn it into a bag or a jacket, for example, or recut it for a different boat, once that sail falls in quality below what's termed grade 4 by Sail Exchange, it stops being usable as a sail. And globally, somewhere around 1% of all the sails that come offline every year are then recut. So it does mean that we're seeing somewhere around 2,000 tonnes of sails are reaching landfill or incinerated or in long-term storage prior to landfill or incineration annually. So this was the challenge that we'd started with. So to address this, we need a recycling solution which was capable of dealing with both the woven textiles and also the solid composites. So to achieve that, we've been modifying a superheated steam recycling system called Decom, originally developed by B&M Longworth. And, excuse me, the nice thing about this system is it's relatively input agnostic in terms of its ability to recycle these input polymers. So if you can tailor the process conditions, then what you end up with is a system which can deal with wind turbine blades, for example, as demonstrated in emphasizing, polyesters, nylons, and quite a large range of other synthetic polymers. And because you can tailor the process conditions, what you can end up with is an ability to strip out the fibres from that system. Shown here, the carbon fibres from an RC44 race cell. And we've removed the resin into a different storage location, retained the fibres, and turn these fibres back into, in this case, coasters for structural integrity testing. And these fibres conveniently have very low or no impact compared to the fibres we put into the system in the first place. So we've not dropped, we've not downgraded the, in this instance, carbon fibres, which does mean this is a much more universally applicable solution to particularly quite complex inputs. And conveniently, our preliminary LCA data shows that this system operates at an equivalent or lower carbon footprint than for carbon fibre, than pyrolysis, which is our other standard industrial recycling solution, or compared to landfill or incineration for polyester-based inputs. So, about this time last year, we'd finished demonstrating that this technology was usable for recycling carbon fibre sales, and we're looking to expand this out into more of our classic woven and laminated polyethylene terephthalate sales. So, this is the point where potentially there was a real space for integrating a biotechnological valorization approach to our recovered monomers, in this case, terephthalic acid and methylene glycol. Because if we remove our resulting monomers at different steps in the system, what we can potentially do is have an aqueous solution at relatively low concentrations, depending on process conditions, of TPA and EG in an aqueous solution, which potentially lends itself quite well to an industrial biotechnological solution to improve the value of these monomers. Because currently, our alternative solution would be to either resynthesize that PET or to sell off the monomers. And these monomers are commodity chemicals. They're very low value compared to some alternatives, such as, in this instance, having a quiet conversation with Jo and working out where potentially we might be able to go with this, with some of the work she developed previously. So at this point, I'm going to hand over to Jo to give you a little bit more detail on her integration of this particular system, the DECOM system, with an engineering biology-based approach.
Thanks very much, Jo. That's a really nice sort of first half, I think, to the talk to kind of set the scene for what we were doing in this project. So as Jo mentioned, we were having a situation where we've got these very sort of high concentration of terephthalic acid solutions from this DECOM process. And this kind of came at a time where we'd actually recently published a paper where we developed a new microbial strain which was capable of taking PET-derived terephthalic acid, which we call TA in this scheme, and we were able to feed this into an engineered E. coli cell and actually produce vanillin as a product. So a kind of way of upcycling plastic waste into a higher value chemical product. Now, vanillin was of interest because it's actually got a market demand of about 20,000 tonnes every year, and only 1% of that demand is met by extraction from the vanilla plant. It's physically not possible to extract 20,000 tonnes of vanilla from plants. So 85% of that demand is currently coming from oil, and there's actually quite a big sort of drive in the field at the moment to develop more sort of sustainable methods to move away from dependence upon those finite fossil fuel feedstocks. So we were interested in developing a method to make it from plastic waste. So this is the pathway that I came up with for the chemists in the audience. So essentially you were going from terephthalic acid, which is on the left there in this sort of cell diagram, through to a key intermediate, which is protocatecholic acid. And this is then methylated to produce vanillic acid, reduced to give the aldehyde, or you can actually do the methylation second, so you can go via this other intermediate. And either way, you get through to vanillin. And just a note here that we were doing this in a strain which is engineered to accumulate aromatic aldehydes, because E. coli natively has machinery to mitigate sort of aldehyde toxicity through reducing it to alcohols. So we had to choose a special strain of E. coli which had a lot of these enzymes knocked out so that we could accumulate vanillin. So Joe, could you move on to the next slide, please?
Yeah.
Thank you very much. So what we were hoping to do at this point was to take that existing pathway which we had demonstrated with kind of post-consumer PET from a plastic bottle and apply it to this new to us waste stream, which is coming from post-consumer sales, end-of-life sales. And as Joe said, we've got about 2,000 tonnes of this waste stream being produced annually, and about 80–90% of this by mass is actually PET. So Joe very kindly provided us with some samples. We call it sale soup in the lab. My students like the different colours that it comes in. And the first thing we did was to analyse this by HPLC to figure out just how much terephthalic acid was in there. We received 3 different samples. So this is just the HPLC chromatogram of those 3 different samples. The big spike in there is caffeine. We use that as an internal quantification standard, so you can kind of ignore that to some extent. But the important thing in here is this third peak, which is TPA, which is terephthalic acid. And you can see that that is the most abundant compound within that sample. And we also see a little bit of MHET, which is sort of incompletely hydrolyzed product, and also BHET, which again is slightly incompletely hydrolyzed. And we actually treated this sample with sodium hydroxide to sort of further that hydrolysis, and we were able to then get through to about 5.5 millimolar terephthalic acid in one of the samples. What we wanted to understand was, could we treat our engineered E. coli cells with this material, and was it toxic? We were really pleased to see that we didn't see any sort of significant change in growth rate in the presence of this sale-derived terephthalic acid, in comparison to either no terephthalic acid present at all, or kind of pure commercial terephthalic acid. So that was quite an encouraging starting point for us. That was at 1 millimolar, which is the concentration at which we tended to do these assays. And then, thanks, Joe. And then the final bit of this for us at that point was to then feed this into these engineered cells. So the first we wanted to do was just to see if we could make protocatechate, and that is the key intermediate in our vanillin pathway. So it's a very good marker of whether or not it's accepted by cells and whether or not it's able to be upcyclable. And we were really delighted to see that we got pretty much 100% conversion of the terephthalic acid from sales through to protocatechate. So you can see on the left there, that's the HPLC chromatogram from the sale-derived terephthalic acid input. And in the middle, we have that from the commercial terephthalic acid, which was our positive control. And you can see they're all but identical. So that was a really nice sort of starting point for us to think that we can metabolically upcycle this sale-derived terephthalic acid to produce useful molecules. And it's worth noting that PC is a useful intermediate, not just to make vanillin, but also many other sort of high-value small molecules that we have pathways for developing in the lab at the moment. So the fact that we can make quite a lot of that is really encouraging, that can then be siphoned off into various other molecules to support a more sustainable chemicals industry. And then the real test for us was, can we go one step further and can we do the whole vanillin pathway? And this is just our sort of preliminary data on this work. We have now received further funding to really intensify this work. We'll go into that in a second. But this was just the first experiment that we did. And we were really pleased to see that we were able to obtain some vanillin when we introduced the rest of the pathway. And actually, sorry, Joe, could you just pop back?
Sorry.
Thank you. And actually, when we compared this to inputting commercial terephthalic acid into the system, if you look at your product distribution as a kind of percentage of total mass balance, those 2 fingerprints were absolutely identical. So we're really not seeing any sort of noticeable difference when we use sort of genuine post-consumer waste TA versus the commercially available stuff. So that's a really encouraging result for us. And Yep, that's fine. Joe, do you want to take over at this point?
So the nice thing about this, we already know, based on our modifications to the decom system, that we can actually recycle 99% of all cells currently on the market. But also, actually, if we can integrate a biotechnological valorization step, we can potentially actually bio-upcycle an awful lot of this recyclate and produce relatively high value commodity chemicals, even at lab scale, as this is potentially a really interesting integration of a couple of different approaches to address quite a large scale problem globally. So since then, we've managed to get some money from iBioIC as part of their Flex Fund to look at upscaling this process somewhat from Joe's original lab scale systems in Falcon tubes at 0.5 mil, all the way up to kind bioreactors, so 15 mil scale, and combine this with optimizing our processing conditions within decom to provide more up-to-date life cycle assessments in terms of the carbon footprint of this whole process, hopefully, as well as a better idea of a more scalable techno-economic assessment. In addition to ongoing systems optimization, optimizing the strain, optimizing the fermentation conditions, and the associated biocatalysis within that cell. So that brings us very much to the end of our presentation. Just a brief thank you to all of our collaborators and to our funders. And if you have any further questions, you can find Sustainable Sailing at the various media outlets shown on the left-hand side here, and Joe's lab shown on the right-hand side. So thank you very much for listening.
Thank you, Joe and Joanna. Really great presentation and great examples about what is possibility with engineering biology. And once you have the microorganisms in place and the right pathways, you can basically produce everything, I think. We are now coming to our panel discussion and Q&A session. So if I could please ask all the speakers to put your cameras back on so we can see you on the screen. I'm going to hand over to Dr. Lynn Wilson, who has kindly agreed to share the panel discussion. And there's some really great questions in the Q&A box. Over to you, Lynn.
Thank you very much, Dana. That was an incredible session. Wow. So much knowledge, so much development in the sector. It's just so exciting and really lots to discuss. So thank you so much to all the speakers. And I did have some questions myself, but actually there are some great questions in the chat and I'm aware of time. So I'm just going to start with questions in the chat. And if the person who has raised the question, if you'd like to raise your hand and come in, if there's a further question, please do. But the first question is from Sam Taylor, and it's for Cindy and Flor. And she's asking, are you only working with UK end-of-life textiles? And are you looking for brand partners with a global customer base? Thank you.
I'm happy to take that one. Sam had started typing a response to that, so I'll just dive in verbally. So what we're doing is focusing on diverting the non-rewearable textiles that are generated here in the UK away from export and from landfill. So our focus is on getting the NRT produced here or generated here into ATSPs to be separated, sorted, and pre-processed into materials for recyclers. Now, those recyclers, we have very little fiber-to-fiber recycling here in the UK, but we expect that with the onset of ATSPs, the landscape and the foundations will be laid for more mechanical and chemical recyclers to set up shop and build industrial scale plants here. So we really see this transition of what's happening to NRT today, going into these new processes, producing raw materials that can then go back into global supply chains. And absolutely, we are working very closely with brand retailers because their supply chains are global. They're manufacturing into fiber, textiles elsewhere around the world, and we need to bring the two together, the sort of end of use together with the manufacturing production supply chain. So it's a local solution or a regional solution when we're looking at collection and pre-processing of materials and turning them into raw materials, but it's very much a global solution where we need all key stakeholders involved in transitioning to getting these materials back into the beginning of production.
Thank you, Cindy. Sorry, so can I just clarify there? So at the moment, you're not looking for extra partners right now at this stage of the project?
Oh, okay. We might want to clarify for the project itself. I'll let Flor answer that. I think for anyone interested in building on this and getting involved, absolutely get in touch. There's a collaborative nature to the project. There's a commercial nature to actually taking this forward after the project. So we are, Circle 8 is the company that's focused on raising the investment and scaling and building, commissioning the first large-scale ATSP. So we welcome, all key stakeholders to get in touch and get involved. But in terms of the project, I'll hand it over to Flor on how to get engaged.
Yeah, so in terms of the project consortium, it is now closed because we have already kicked off the project. But as we have mentioned in the presentation, there are opportunities for brands and retailers and other organizations outside the project consortium to collaborate externally with the project. But the project consortium as such, it is closed. But again, trials, participation in workshops, roundtables, it's something that will be open to organizations outside the project consortium. So I will say that if someone is interested in engage with the activities within the ACT project, they can drop us an email to the sustainability@ukft.org, and then we can take it from there.
Thank you, Flor. Because Cambridge consultants, they are also asking, but from a technical point of view, are you interested in additional collaborators for technical developments? Would the same rules apply in terms of interest is closed at this particular project?
Well, I would actually say on that one, so we're working with MTC here in the UK, the Manufacturing Technology Centre, who are our technology partner guiding the process and the development. And they are looking at all different technologies that are out there on the market, doing a market review of that, which is about to be finished, but it's an evolving landscape. So definitely get in touch with us offline, and as well we can make an introduction to MTC, because this is such a new space when it comes to automated sorting. There's lots of different components to it. There's AI that's going to be constantly improving. So anyone and everyone who has any expertise in this space, we want to be talking with you. So do get in touch. And we can continue the conversation.
And the questions are sort of grouped in terms of the point that the speakers were presenting, and so I'm just going to carry on in that way. So the next question again is for Flor and Cindy, and from Alan Wheeler at the Textile Recycling Association. He'd like you to expand on what we need in order to expand the demand for recycled content, which currently still remains very low.
Flora, you're not going off mute, so I'll take that as an indication for me to take this one. But please jump in. Yeah, hi, Alan. I mean, in some ways, so if we're looking looking at chemical recycling and the outputs from chemical recycling being equivalent in quality to virgin materials, I don't see this as a demand issue, because everyone who demands virgin materials, there's no reason why you wouldn't start replacing those with circular materials. Certainly in the case of polyester, where you get a like for like quality. You know, in the case of cotton to cellulose and chemical recycling, it's a displacement product for cotton, but equally it's compatible or comparable to cellulosic pulp being spun into cellulosic fiber and viscose. So I think it's less of a, we need to get over this kind of mindset that it's a new product. There are challenges with it. There's certainly, it could be down to price. It could be down to, you know, having to reshape supply chains, but all of this is possible. So I think the conversation should be around the infrastructure change that needs to happen, the change in supply chains, and those conversations versus should we have demand for recycled content? Absolutely. I mean, it's high quality. Mechanical recycling, slightly different case, but equally there's a role for it in many different product ranges. So I think we need to increase the conversation around that and find out what those blockers are, because the demand for raw materials is there. So we just need to find the solutions for really integrating them in high volumes. And also chemical recycling is so much at the early stages. It's just not available in high volumes. So a lot that needs to shift, but be really good to hear some views from the audience as well, because I think it's a hot topic.
Thank you. Thanks, Cindy. For the moment, that's the questions for yourself, but I'm sure people can keep putting them in the chat. I think it's just because we have so many participants online that I'm sort of going through the questions to give the speakers the opportunity to give a full response. The next question is from Rachel Klaus. Hopefully I pronounced that correctly, who has a really exciting innovation in terms of bio-based sequins. But she's asking, would a bio-based plastic be less bad at the end of life than a synthetic plastic? I think that's a really interesting one in terms of for me, the whole challenge of landfill. As soon as you put anything that's not in an end-of-life system, it's going to be a pollutant. So who would like to take that one? Cindy, are you able to answer about bioplastics, or is there another participant? Professor Du? Is that perhaps?
Okay, yeah, I think we probably can answer some part of it. So we did some life cycle assessment on the different technologies. So in terms of the bio-based material, I think the mainly benefit is the production part. So in the production of the bio-based material, we're using less energy normally, and also the productions do not involve the, let's say, dig after the crude oil things. And so from life cycle point of view, definitely bio-based material will be beneficial in general. It certainly depends on different cases. From the end of life usage, I think normally the bio-based material are relatively easy to break down. So from that point of view, it will be beneficial for the environment, and then ideally the bio-based material will be easy to recycle instead of landfills or incineration. The biomaterial are relatively, in general, easy to be recycled through either chemical recycle process or biorecycle process. I think, yeah, it have a good potentials, but certainly depending on different materials. Yeah.
Thank you. Rachel, I hope that's answered your question or expanded on it. Please come back in the chat if you have additional questions. Moving on to Joe and the recyclable sales. Kevin Hallis has a very simple question. What does the economics look like? Which Joe would like to answer that really succinct question.
So the economics from a sustainable sailing perspective are quite straightforward. We're a for-profit company. Currently, you can hire a bin from us for a specified input. So, for example, Dacron or carbon or nylon sails. And then at the point where you've filled that bin, we'll pick it up from you and we'll recycle that through the process. And the money you've paid to hire the bin in the first place pays for the recycling, and the subsequent resale of the commodity chemistry means that ultimately we run on even at a kind of ton per year, we're running at a reasonably kind of sensible profit to survive as a company. The economics subsequently of the metabolic upcycling is a little bit more complicated for the simple reason that it's quite small scale at the minute. So I don't know if Joe you want to talk in a little bit more detail about that.
Yeah, absolutely. I mean, as Joe said, this is very sort of proof of concept stage for us at the moment, and whether or not it becomes economically feasible will really come down to how much product we can produce in a kind of given space time frame, you know. And at the moment we're doing a lot of strain engineering, so we're also working with another industrial partner who are involved in sort of vanillin production, and with them we're doing quite a lot of strain engineering as well. So I think it's really going to be a combination of this kind of input technology. So we have a waste stream of terephthalic acid rich waste stream, and then how efficient we can convert that through to vanillin. So I think it's too early to say at the moment whether it's, you know, what the economics are going to look like, but I think certainly compared to existing like lignin processes, which produce kind of quite a complex mixture of products, which can be quite tricky to separate, this in comparison gives quite a kind of pure product profile of vanillin. So I think the downstream processing costs could be competitive on that front.
Thank you, Joanna. Just when you're there, we have an anonymous question. Can you just remind us who this research was funded by? Thank you.
So this specific piece of research, I'm not sure if I mentioned it at the time. This was funded by the Department for Transport and Connected Places Catapult as part of their Transport Research Innovation Grant 2022-23. And that was all funded by the collaboration.
And we are now continuing the project with support from iBioIC. So we're very grateful to them as well.
Thank you. And for both of you, another quite technical question. Did you look into the life cycle of a sail going into PC and vanillin, and in whether or not this makes commercial or sustainability sense from a circularity perspective? What are the advantages compared to, for example, recycling it into? And my question is, I'm not sure if it stops there.
Recycling into new PET, I think, is the end of the question.
PET. Right.
So we did an LCA of the decon recycling system for PET-based inputs and for Dacron and Mylar sales in this instance, so polyester-based sales. And that, because it's a large back scale process, which has a relatively straightforward efficiency gain at scale, we can demonstrate that on a carbon footprint basis. Once we're at a kind of commercially relevant scale, that operates at a lower carbon footprint than putting the same sail into landfill and just leaving it for potentially the 500, 800 years that it's going to take to degrade. We haven't necessarily applied that then to the metabolic upcycling approach, largely again because it's quite small scale. Well, it's very small scale at this point, and it's obviously now in the process of scaling that up slightly. One of the potentially quite interesting things from an LCA perspective would be the displacement of existing sources of vanillin by this particular source, largely because things like petrochemical synthesized vanillin, depending on the life cycle assessment, can have enormous carbon footprints relative to quite small production scales for vanillin. Some authors are attributing this to up to kind of tons of CO2 equivalent to produce kilos of vanillin. So comparatively, we'd hope to be lower than that because we're not having to dig it out of the ground, and then subsequently go through quite a complex synthesis pathway. But again, it's quite small scale, so we'll work out in slightly more depth and slightly more detail what that's potentially going to look like later.
Thanks, Joe. They just keep coming. We have another question for you from Gustavo, who says, I'd like to ask Joe about the pyrolysis they have used for pre-treating the sails. Have you tried to extrapolate this pre-treatment to polyester textiles? Do you have any idea of what could be the outcome of this pre-treatment for textiles?
So it's not strictly pyrolysis. It's the British Standards Institute terms decom as a pressolysis-based system. So a pressure-based lysis of the input polymers. Practically, in terms of the kind of functional chemistry, there seems to be quite a lot of stuff going on at the same time. We have not directly expanded out an LCA or a TEA to polyester-based textiles in this particular format, but we'll have some stuff coming out via sustainable sailing in the next couple of months around potential other applications. So I'm unfortunately not going to be able to give you a particularly in-depth answer just at this exact moment in time.
Thank you. And a question now for Professor Du. Is there scope to do combined, and that's from Deepan Shah, is there scope to do combined enzymatic digestion with cellulose and PET acids to get both sugar and TPA from the same process?
Yeah, I think definitely that's something we could do. I think, yeah, for the definitely, I think the enzymatic hydrolysis conditions could be slightly different for the cellulase hydrolysis and then for the PETase hydrolysis. But certainly, if we could combine this enzyme together, it could help to break down the network further, and then these two enzymes, if they are optimum enzymatic hydrolysis conditions are similar, so we could try to put them together and then to facilitate the further degradation, both cotton fibers and then PET fibers at the same time. I know there are quite a lot of development on the PET case recently. There are quite a lot of technical advance in this area. I think there are certainly scope to do that together.
Thank you. And we have another question for you from Gustavo, who asks, what's the maximum hydrolysis of cellulose from cotton when using fungal enzymes and a blend of cotton PET? Have you tried to evaluate the influence of the dyes and additives on the cellulose activity?
Yeah, for the first part question, from our own enzyme, we can reach about 90% if we really want to hydrolyze all the cotton fibers into glucose. So we can reach that. I think compared with the commercial enzyme, they blended a different subunit together. For the enzyme we produce, we produce the enzyme from a single fungal species that lack for a certain type of subunit of the enzyme. So if we add other enzyme into that, we could achieve a quite high, nearly complete degradation of cellulose into glucose. Regarding the dye additives, so our previous first generation process, we're using post-consumer products, so we don't know what's the dye type and then how much dye they added in, but we do observe different dye methods have a different impact on the enzymatic hydrolysis. Let's say the indigo dye are quite bad for the enzyme. So in general, so the dye will inhibit the enzymatic hydrolysis process. In the next step development, we have collaborators, and then we can directly add the dye into the textile products in a controlled way. In that case, we would be able to investigate scientifically the dye impact on enzyme and different dye impact on enzyme.
And just one final question for yourself, and I think you may have answered part of this, I'm not sure. Where are the enzymes grown or sourced? Do they depend on other raw materials? And what are the waste outputs of the process, and how are those handled?
So we produce enzyme on different materials. So when we do the bioethanol fermentations, we produce on the other biomass. When we do the textile waste, we consider, let's say, the enzyme grow on the textile waste that they already been tuned and then adapt themselves to get the correct site of enzymes suitable for textile waste degradation. So this is why we want to using the textile waste to cultivate the fungal to produce the correct type of the enzyme. So sorry, what's the next part of the question? I think pass by. Yeah, certainly depending on different raw materials, the fungal microorganism, they produce a different type of enzymes, and then the waste output of the process. So the waste, we want to use everything, and then there's small amount of waste left over, and then in the second generation of biorefining process, we want to, let's say, go through the incineration process and then to recover the heat and the power, but it will be a small amount. So we want to recover, our target to recover 80% of the PETs and then 80% of the cottons, and then into new fibers, and then into new textile application.
Wow, and we have a final question for you. When producing small cellulose molecules, do you only use endoglucansis or a mixture of cellulases produced from the different strains? And how are you respinning these molecules into cellulose fibres?
So this what is ongoing research. So that's what we want to investigate on the second stage of the process. So yeah, if there are some kinds of progress, I think we will report it in the next few probably months, next few years.
Thank you. So that concludes the questions in the chat. I would like to ask each individual speaker one question, and that is, if you could tell me, where do you think we'll be with these technologies? Where will we be by 2030? And maybe if I could start with Cindy.
Thanks, Lynn. Thanks for dropping that on us. Where will we be? Well, it depends on how quickly the industry acts, gets involved and starts implementing. And I feel like we have a whirlwind or a momentum like we've never had before. So I am quite positive that together with the incoming legislation that we are going to start seeing some change, but also with new technologies, until you have them, there's not a lot you can do. So I do think that as we start seeing a few industrial plants popping up, it will really start driving that change. So by 2030, I'd like to see that at least half of our non-rewearable textiles are going into processes. I know that's probably over ambitious, but I think if we put our minds to it, we get the investment community on board, we get the brands and retailers saying and showing the market demand through offtake agreements with recyclers. You know, all these things need to come together to really drive it. But if we put our minds to it, I think it can happen.
Thank you. And yes, of course, I was just asking you for your wish more than anything, Cindy. Joe or Joanna, what about your sector? Where do you think you'll be by 2030 with the technology? Where would you like to be?
Well, I can answer that if you like. Firstly, from the sort of biotech R&D side of things, I would say that I feel really optimistic about this at the moment. The field of waste upcycling using kind of engineered microbes is absolutely exploding at the moment in a really positive way. And we are seeing an unprecedented number of examples of taking post-consumer waste from the textiles industry, but many other things besides, and upcycling that into a whole host of products. I think the sort of things that are coming out of science in terms of the tools that we have at our disposal to actually do this is really an expanding toolbox. Every month we're getting new enzymes. There's huge metagenomic databases that are giving us really exciting tools to build into these rationally designed systems. So from the scientific point of view, I think even in the next kind of 6 years from 2030, I think we're just going to really expand the scope of what we can actually do with these systems, which will then hopefully have input into sort of a wider variety of kind of industry sort of final users. So yeah, I'm feeling quite positive about it. I don't know how that fits in with Joe's perspective from the more industrial standpoint.
I'm also actually really positive about it, particularly over the last even the last 6 months, the difference in conversations we've been having with people, and difference in terms of policy that we've kind of seen coming down the line, in terms of conversations with customers, investors, and suppliers. The kind of end of life solutions for end of life and closing the loop on different input polymers has taken off to really kind of a really exciting degree. And if we can combine that with all the really exciting advances in the kind of biotech world, particularly kind of extracting things out of the lab and applying them to a slightly more kind of industrial scale, I'm really hopeful at this point that in the next kind of 6 years we're going to look back on this period and go, wow, we had no idea what was coming. That was really cool.
Thank you. And Chen-Yu, where would you like to be with your technology? What would be your wish for 2030?
Okay, I think from the recycle point of view, I think the whole textile and the fashion industry, they really move forward towards the recycle economy. I think I attended several textile conference recently. I think the focus of the conference shifted from the fast fashion and then new material towards on how we can recycle. It's really a trend from the whole industry towards about the recycle technologies. For the technologies we want to develop, hopefully in 6 years, we want to achieve the stage that is at the current stage, we want to go for the demonstration stage. I think by about 6 year development, we will be able to set up some demonstration plan and really have some trials about the technologies in the UK, and then to make great impact in the industry.
Thank you very much, and thanks for your response, all of your responses to the question. But we do have one last technical question from Martin Riley, who says the commercial process used at Colourfix depends on distributed enzyme manufacture, the ability to generate large amounts, 300 litre to 3,000 litre batch fermentations of enzyme on site, anywhere at very low cost. Do the panel see application for this capability in other areas? Who would like to take this question first? Chen-Yu, would that most apply to your work?
Yes, I think so. Yeah, let me read the questions again. Yeah, I think the enzyme cost is, let's say the cellulose enzyme production cost reduced dramatically about let's say 20 years ago when we first start to look at about cellulosic bioethanol. The enzyme costs are significantly high. They contributed more than 20% of the overall production cost. Along with the technologies, I think the cost reduced dramatically. And then nowadays, I think less than 5%. So this reduced by a factor of 4 or even more. So I think along with the technologies, I think there is a scope, let's say, to using the technologies and then to working on the process, especially for our applications, we not target about the complete degradation of the cellulose. We want to just degrade to a levels that achieve our target. So we don't think we will use a higher amount of enzyme. I think the technology do have a financial, have economic feasibilities to have a large-scale application.
Thank you very much. And that concludes our questions. Thank you very much to iBioIOC for the opportunity to host this question session. And I think that my takeaway, the most exciting thing is what Cindy just said, momentum like we've never had before. And I think from this conversation, we can really see the depth of focus on the challenges. So thank you very much, and I'll hand back to Dana. Thank you.
Thank you, Lynn, for sharing an excellent panel discussion and some really great discussions and questions from the audience. Thank you so much for everyone taking part, and to all our speakers as well. I just want to highlight some potential upcoming funding, because it's always, quite nice to have some funding in the pipeline. So they are not announced yet, so we're waiting for final confirmations, but there might be funding from Innovate UK around reimagining materials and manufacturing. So it will be a feasibility competition round 2, and it's supposed to be live in April, beginning of April. And then there will be or might be a second round of calls for the UK launchpad for bio-based manufacturing in Scotland. So look out for any news on this. And then there is some feasibility funding coming from iBioIC, and you heard from Joe and Joanna, how their projects have been funded by iBioIC funding. And this will be up to 30,000 match funding for industry-led collaboration with Scottish HEIs. And then some events in the pipeline. Kim already mentioned the textile fashion event on the 13th of March at Glasgow. And then we have a material research exchange coming up on the 23rd and 24th of April in London. It's all about materials, what kind of materials, what innovations are happening in this space. And then also, if you are working on open innovation, if there are any challenges you have where you might be looking for partners outside of your usual network, come and talk to us, and we can explore how we can help you. And our contact details are on the screen, so please get in touch if you have any questions. Kim, anything you would like to add?
No, all good, Dan. Just a big thank you to everyone for some fantastic contributions today. It's been a great session.
Good. Okay, thank you, everyone, and enjoy the rest of your day. Thank you.
Thank you. Bye.
Thank you.